Okay, so this video is going to be on uncertainty analysis and looking at repeatability of data, mean, average, standard deviation, some of those definitions that maybe, hopefully, you've heard in other classes, so that when you're reporting results, how many significant figures can you report that result with? What's your error bars in it? Okay, so rule of thumb, when you're taking data, you want to repeat that measurement 3 or 4 times. If you have someone else that can do the same measurement or even a different lab, that verifies it even more. And then more times you repeat it, then the more sure you can be on the number that you get. Okay, so what we want to do is look at how you can quantify the error in that measurement. So here's a couple of different just definitions. So let's say X is the true value, so like the temperature in this room, and we measure it using some device, and maybe our measurements are kind of scattered around and they're not exactly what the true value is, but they're close to it. And n would be the number of measurements that we take it. So we measure it, we walk to another corner of the room, we measure it again, walk to another corner, measure it again, hand it to our lab partner, and they maybe use some slightly different technique to measure the temperature. And so you end up with n data points, right? So here's two words, accuracy and precision. So right here, if this dark dot in the center is the true value, and then these crosses are the data points, at least this black dot is kind of in the center of it. So for this one, you'd say this has good accuracy, but bad precision. So precision is how close the grouping is, and accuracy is, does the average of these values actually match what the true value is? So this is good accuracy, poor precision, versus over here, we have a good grouping, so that would be good precision, but it's not grouped around what the true value is. So maybe there's some kind of a systematic error in taking data in this situation that just keeps giving the same error over and over again. So you think you have some nice results, but actually you're not really what the true value is. Another question to kind of ask yourself is, how would we know what the true value even is? So how do you know the temperature in this room, or how do you know the pressure, or we can only know what we measure. So that's the frustrating thing, is you actually never know the true value. The only thing you can ever understand is the average of the data, and every data point is going to be off. So the true value is kind of this mystery that you never really know, because you can only know what you measure. So that's another kind of sad thing. I mean, the more measurements you take and more labs take the same thing, and you can get pretty confident in it, but you never really know the exact true value of anything. Okay, mean, mode, median, and these are some things that we'll use these functions in Excel, and so it's really important to know what equation goes with what. So mean is kind of the average of the thing. So x sub I, that's each data point, and n is the number of data that you've taken. This is a summation sign. So if I take this data point, I'm going to add all those values together, x1 plus x2 plus x3 plus x4, and then divide all of those by the number of points it's taken. So that's what that is. The median, if you line them up, kind of sort them from smallest to largest, and just find the very midpoint in event, that would be the median. And the mode, let's say I take 100 data points and 30 of them all fall on exactly the same value. So that would be the mode, and you'd see that coming out when you're using like histograms. Okay, so mean, median, mode. We'll use the mean here, and it's represented with the symbol with a bar on top is usually what you use for averages. Okay, the error, this is the deviation from the true value. Okay, so if I look at the distance between my average, which we don't know the true value, but we can figure out what the average is, And we just take the distance between each data point and where that average is. So we're kind of looking at how large of a scatter that is. That's what's going to define kind of our error bar. If you report your number and you say, oh, this is 30 plus or minus 5 degrees. Well, that plus or minus, you're trying to somehow quantify what the error in measurement is, so the precision of it, if you will. Okay, so what we're going to do to quantify that scatter is use something called the standard deviation. And if you ever take a statistics class, you'll see a lot of this with normal or Gaussian distribution. We'll talk about that. So what we're doing is we're taking the difference between each measurement and what the average is. This little u, that's another symbol for average. And it's kind of an a squared plus b squared equals c squared deal. So we're going to square this and then divide by the number of data points minus 1. And I'll walk through one of these calculations in Excel for you so you can see this calculated out. But the idea here is we're going to quantify the distance between each of these individual points and where the average is. So again, that would be your precision, just how large the scatter is and what's the average distance away that we are for each of these points. And so here's the equation. And again, Excel has a built-in function that does this, but you really want to make sure. So there's standard deviation of the mean, the basic standard deviation of the mode. There's all these different standard deviations. You know, really want to make sure that the equation you think is happening in Excel's function is actually what you're expecting. Okay, so talking about standard deviation, and this is used over and over and over again, it describes the shape and width of Gaussian distributions, normal distributions. And this would be like if you take the same measurement 100 times, and a lot of the measurements will end up at some average. So maybe the average is around 0, or maybe the average is down here, but then you'll have some outliers, right? So maybe some of the temperatures will be higher and some are lower. And depending on how easily it is to take that data and how repeatable it is, you'll get different shapes of these curves, but they'll all be kind of this bell-shaped case, a lot of them anyways. So this is a very common distribution. Maybe I'll show you a little example. Let me just pause the video here, and then I'm going to get out a toy to show you. Okay, so what we have here is a Galton board, and trying to zoom in on it, there's a bunch of little round BBs, and they are going to fall out of this container here and hit all of these little pegs. And each peg it gets to, there's kind of a 50-50 chance it'll go to the left and the right. So it'll kind of scatter as it bounces around in here. And then after getting sort of randomly scattered, the little ball bearings will fall in these slits, and it's going to create sort of a histogram underneath to show the random scatter of the ball bearings. So here we go. We're going to flip it upside down. All of the ball bearings bounce around chaotically and fall into the little slots, and you see a line drawn there. Interestingly enough, they will repeat the same distribution. So very chaotic system with random bouncing around is creating a reproducible distribution, a reproducible histogram. If we zoom in on that a little bit here, let me show you what the final result is. So it's kind of a real live histogram, it's repeatable, which is good news that all of that chaos can add together to something that you can describe the width of and the height of and where the mean is and the average. And this is what a lot of different data sets will form this kind of curve. Okay, back to our note. So here's this Gaussian distribution, and what does that have to do with standard deviation and mean and mode and the stuff we were calculating? So the tallest point, that is going to be the average. And if you go out 34% on each side, that is 1 standard deviation. Another 13%, that's 2 standard deviations. 3 standard deviations. So that would mean that like 99.99% of everything would fall in between that 3 standard deviation. And this little guy, this is a sigma. So the mechanical engineering certification, you'll say 6 sigma, that you want everything coming off of that factory production line to be within 6 sigma of that standard deviation. So you can have narrower distributions or wider distributions. Again, that's going to have to do with the precision of the data, how well the grouping is. And the more samples you have, the more defined that average is going to be. In fact, if you have lots and lots of samples, you get what's called a Dirac function, where you basically get a line and everything is right here at that one value. But when you report a number and you say plus or minus 5 degrees or plus or minus 3, what you're describing is how wide this distribution is. So you're telling your user what your standard deviation in that data is. Okay, let's go ahead. I'm going to open up an Excel file here, and let's say how we're going to apply this to maybe the data that we're taking. So what if we are loading our sample of material? We measure the force we apply to it, force divided by the cross-sectional area. So that would be stress. It's like kind of pressure, force over area, pounds per square inch or newtons per meter squared is a Pascal. So we have the applied force, and when you apply that force, it's going to stretch out the material. So this is strain. This is change in length divided by the original length. This is actually unitless, so it can be change in inches over inches or change in centimeters over centimeters. It's just the fraction that we're getting here when we measure strain. And when we plot stress versus strain, so you add a little bit of force and it stretches it out a little bit, add a little bit more force and it stretches it out a little bit more, all the way up to what's called the yield strength. So initially, a lot of materials will deform in a linear fashion. This is called the elastic region, or the, and this is really what you want to design for. It's almost like F equals kx for springs. So force is linearly proportional to how much you stretch the spring out. And this initial rise over run, the slope of this linear elastic portion of the stress strain diagram is known as the Young's modulus. And this slope, to see how repeatable of a slope you could get, that would be a good thing. After the yield point comes plastic deformation. And this is permanent deformation. So if I loaded it up with that force and I applied that big load onto it, and then I let go and I let it snap back, it would be permanently bent out of shape. It would actually follow kind of a similar curve back. So the same slope, but it would not snap back to its original shape. So we say that it's broken after this yield point. Sometimes you think, oh, it's broken when you see 2 different pieces, that it's shattered into pieces and fractured. But a true engineer considers it broken after the yield strength, because then it's not snapping back to its original shape, and you don't want to design anything past the yield strength. In fact, you're going to use a safety factor and not put any load on that part that gets anywhere near that yield point. So this is a characteristic. A lot of metals follow this behavior. So if you have something brittle, you would have a very steep slope with not too much of a plastic deformation. It would just suddenly shatter into 1,000 pieces. Versus if you have a ductile elastic material, then it would just take a little bit of force to really stretch it out. So you'd have a lot of strain, a lot of stretching with very little force for a ductile material, and then somewhere in between. And you don't want a brittle failure. Brittle materials tend to be stronger, but that comes at the expense of you don't have any warning when the thing is going to break. So it just all of a sudden it cracks and you have a disaster. You want to see it kind of bending and struggling and say, the bridge is going to break before it actually goes. You want a lot of warning. And so somewhere in between those two extremes of brittle versus really ductile and elastic gives you your best materials. And there's a whole science in metallurgy of how to, develop alloys and heat treatments that will give you the strength properties that you want in a material. And for your rubber band experiment, actually, you can treat that material. And I think I told you that before, that I'll give you some extra credit if you can figure out either a chemical treatment or a heat treatment. Use your home oven or boil it in water. You can freeze it. See if you can find some sort of a treatment that would strengthen that rubber. And I will give you some extra credit if you can figure out some ways to treat the material to change the strength properties. Okay, so let's say you take this, you get this awesome graph, and you do the test again, so you get another graph, and then same thing, another rubber band out of the same batch, and you're loading it the same, and you get another graph. And of course, maybe you load it a little bit different from one to the other, or maybe the temperature of the room was a little bit different from one to the other, or one rubber band just doesn't come off the assembly line quite like the other rubber bands did. So one of these graphs does not look quite like the other ones, but you can compare the slopes of each one. Okay, so trial. This is how many times that you're going to take data. And let's say 3 or 4. I mean, you really need at least 4. And I know that's a lot of data to take, but try and get a good standard for this and get one set of data that's going to give you some good numbers. And then we're going to look at the slope of this curve for each one of those data sets. So we're taking a lot of data and a lot of different graphs, and we're kind of condensing that into a very small amount of data that you could put on a report. So the final report isn't going to have all of these data and all this graph. It'll just have the slope of this line, and we'll say, what is our confidence? What is the error in measuring the slope of that line, the Young's modulus, which stress over strain. And remember, our units for stress is force over area, strain is unitless. So this is going to be like newtons per meter squared, which is Pascal. Okay, so let's say we're going to give the Young's modulus for each of these, and we'll use gigapascals for this. And we can maybe look at some other happenstance data, see what other people are getting for, I don't know. So here's like some examples for some different plastics. Polyethylene, high density, or so 2.6, 2.7, 0.8, and maybe we're order of magnitude in there. Okay, so I'm going to just make up some numbers here. So let's say we ran this experiment several times, and maybe we get 1.25 or 1.5, or next time we only get 1.18, and really pay attention to this. So you can say, oh, I remember for this one, I was actually loading it kind of fast or kind of slow, or I had the air conditioning up. So any little details like that you can sort of add some notes and explain why these data are not exactly the same would be valuable. Okay, so from this, let's first calculate the average. So when we say what the actual Young's modulus is, we're not going to say 1.5 or 1.35. We're going to say it's the average of all of these values. And if you remember how to get the average, we're going to add together all of these values, 1.25 plus 1.5 plus 1.18. Okay, so we're going to add all these together, and then we're going to divide it by the number of data points that we get. Okay, so that would be the equation we type in. We're adding these all together and dividing by the number we get. Now there's actually a function in Excel that will do this for us. But again, is it mean, mode, average, median? There's all these different things, and so you want to really make sure that you understand what equation Excel's function is using. So before you just type in average and add it together, you better make sure that you know what that function is doing, because sometimes you can get into a little bit of trouble by just assuming. Never assume anything with this stuff. Always check it out. Okay, so there's our average, and the next thing we want to do is calculate our standard deviation. So when we report our number, we're going to say 1.32 plus or minus, and then describe the scatter. So how precise are our results? How many significant figures should we use? Let me just pull up that standard deviation equation again. Again, we're looking at each individual data point and how far away it is from the average. This is just kind of a way to quantify that. And we're going to sum up all of those little differences. So what I think I'll do here is I'll just take a little chunk out of this numerator. So I'm going to take this little difference here, and I'm going to make a whole new column to just do this difference. Okay, maybe I should format this table a little bit here. Okay, so what I'm doing for this piece of the equation is I'm looking at the difference between each data point and what my average is. And since I'm coming back to the same average for all of these, I will use $sign for that cell. So the red cell, as I copy this equation down, the red cell will be held in place while the blue cell will update. Okay, and that's $signs. F4 is the shortcut to add $signs if you want to use that shortcut key. Okay, so I'm going to go ahead and drag that down. And you can see that the red cell is staying in place because of those $signs, but the blue cell is updating to the new rows as I dragged it down. Okay, so this is that top chunk of that equation. And now to calculate the standard deviation, what I'm going to do is I'm going to take the square root of the sum of all these little guys, and then I'm going to divide through by the number of data points, 4, that's what my n is, minus 1. So actually it's going to be divided by 3. So here we go, equals square root of the sum of all of these little differences, and that's going to be divided by n minus 1. And there we go. Let me just check this again. Yep, that's squared. So standard deviation 0.1388. And again, Excel has a function to calculate the standard deviation, but make sure you understand the equation behind this function, because there's standard deviation of the mean, of the mode. So you want to make sure that you're getting the correct standard deviation here when you type in these functions. So STDEV of this data set will give us the same thing as this equation here is giving us. So for your project and for this next lab, what you can do is set up these equations and these calculations and these tables so that all you have to do in the future is copy and paste your data table and update the data. So let's say I have a new data set where I actually did get numbers, and my numbers were different, right? 1.15, 1.55, 1. Right, so it'll recalculate my average and my standard deviation, and I can get everything formatted well. So if I kind of take time to get one data set set up really well and nicely, I can go ahead. I don't need it in there twice, right? Then I can copy and paste that table to other places. The one thing to be careful of when you copy and paste it over, so like if I copy this over to this new position, I have a problem in that it's grabbing the average over here instead of my new average. So I will have to go through and change this guy to what it needs to be. So be careful on that front when you're copying and pasting equations around. If you have an entire sheet formatted the way you want to, instead of Control C, Control V, because sometimes that doesn't quite get all the formatting. There's a couple little tricks in here of copying over the format when you copy things. So you can say Control Alt V and have a few more little options for what you're actually copying there. Another option is just to right click on the tab and say Move or Copy, and click this little Create a Copy box and say OK, and then you have two sheets. See, now I have sheet 2, and they have exactly the same table set up. So a lot of the work on this before you take data is just getting these tables set up correctly so that when you take data, you can crank in numbers. It'll automatically do the calculations for you. One more thing to add onto this. So what you want to do is you'll have this test. So maybe this is the standard with no treatment. Okay, and this is everything that you did with, it wasn't frozen, it wasn't soaked in anything, it wasn't chemically treated. And then this other one, maybe we soaked in, I don't know, cooking oil for 24 hours or something. So you want to give some details in there, like the time that it was soaking in there, and then maybe you have another test where you cooked it in the oven. But give some details for maybe the loading rate. So entire test took 10 minutes with 1 minute for each data point. Okay, so if you load a rubber band and then come back the next morning, it's called creep, that it will slowly get longer and longer and longer. Even though you haven't added any more weight to it, if you just let it sit there, it's going to slowly stretch out and stretch out. Maybe watch a couple of videos on polymers and what that atomic microstructure. It's like a bunch of spaghetti noodles that are all tangled up. And actually, when the thing breaks, really look at that fracture surface. I don't know if you call it a fracture surface or not, but if you go just right, you can actually see like little whiskers coming out of it. So you can see that those polymer chains. It's kind of neat. You can get a lot from a fracture surface. So if you ever come up to a bridge that collapsed or something that's broken, tell people don't touch the fracture surface, because you can do some microscopy work and get a lot of information about the conditions that the material failed under by studying that fracture surface to see if it was a brittle or ductile fracture and kind of what the forces. You can do a little bit of detective work to see how it broke. Okay, so hopefully that's a good start on calculating standard deviation, mean, mode, what that means, setting up some of those tables, and thinking through this not just for the stress strain rubber band test, but for your own experiment. So maybe you're looking at energy efficiency, or I don't know, thermal conductivity, or you're taking some kind of data and you repeat that measurement over and over again, and you want to turn your final value and know the error in it and uncertainty in it. And a good set of data, it's very tedious to get through. This is, the life of any researcher spends a lot of time meticulously, very, very carefully taking data. But if you want your work to be referenced and used by others and to make new discoveries, that's the kind of lots of work involved with it, is setting up a really solid experiment that isolates what you're trying to understand and taking some really good data. So hope that will help you think through some tests for your project and get started on this next lab.